Welcome, everyone. First of all, how is the energy level? Sabrina, are you happy? Full of energies? Yes, yes, that's what I want to see. Thank you very much for joining. This is a really hot topic, laser beam shaping and laser pulse shaping. There is a lot of room for collaboration here. I think many of you have already seen the supply chain with as many suppliers as providers. Let's find reasons to work together. So we have 2.5 hours to make sure that we all know each other. So let's first start with EPIC. What is EPIC? Well, EPIC is an association of 500 of you, and we are extremely happy for having those 500 of you. I have just two ultra-fast photonics things to tell you. The first one is that this is the 21 already EPIC online technology meeting, and we are so happy with the feedback that we are receiving from you. 558 members of EPIC. Photonics, welcome to EPIC is the last one. So 558 members of EPIC. And for those of you who continue following all these online technology meetings, they notice that every day I announce more members. I am so happy that during these very difficult times, you keep supporting the association. We are doing all these online technology meetings because we need to make sure that you keep connecting, and that soon the time is reaching to the end and we are soon going to be traveling again. So when the situation normalizes, whatever normal will mean, we organize every year an industrial laser event. The next one is in Torino, 20 and 21st of May. We announced 1 year in advance. 20 and 21st of May, I would like to see you in the beautiful, beautiful Torino city at the headquarters of the Prima Electro Group, Convergent Photonics. We're going to have the creme de la creme, all of you talking about the industrial laser market with the key companies from the user side as well as system integrators. I also would like to remind you, many of you are already EPIC members, so you know the drill. All of you have access to a long list of market data. Actually, Carlos is crazy. He counted it, 17,000 view graphs available to you, to all of you. So please make sure you use them, you abuse them. Today we have a lot of optics manufacturers. I would like to let you know that we bought a market report from Joel on the wafer level optics industry. It's actually one of the best reports that we have. Please have a look at it. And if you cannot find it, just contact me or Francesca. We'll guide you through this. We have the biggest website to find a job in photonics, www.jobsinphotonics.com. We have scouted actively all the members, and we know your job openings and put them in this website. For anybody in the YouTube discussion today, if you want to work in photonics, there's nothing cooler than that. Work in photonics, go to this website and find the job of your dreams. That's all I had to say. Now we talk about beam shaping. First of all, I would like to thank our sponsors today. Cailabs, all the way from beautiful France. Cailabs has the best beam shaping technology that I have ever seen. Any shape that you want, actually manufacture products for the telecommunication, for the free space transmission, for industrial lasers, for the local area networks, any beam shape that you need, these guys can provide. Focuslight is the global provider of high-power laser diodes, micro-optic, photonic application solutions. They actually are the ones who acquire Limo, so they have everything that you need for developing the right laser components on the way to the high-power laser diodes. Optoman is the company who makes the coatings for the laser optics, IBS processing, actually high accuracy, repeatability, quality. The guys who actually understand the need. If you ever have the chance to have a coffee with Remy and understand what he can do, it's actually quite impressive. One of the best laser optics that you can find in the world. Asphericon, when it comes to precision, there is nothing better than that. Actually, Asphericon has a novel technology to make optical elements from aspheric lenses to free-form optics. And thanks to the CNC control technology, they managed to have another level when it comes to accuracy of their shapes. An amazing company. I'm so happy to have them at EPIC. PLX, all the way from New York City, all the way from the US, one for American representatives. They develop monolithic optics, actually for many applications, because they're super reliable. They can actually deploy the technology from space, defense, aerospace. So whenever you need beam shaping in a harsh environment, where do you go? You go to PLX. And finally, last but not least, actually I say the best for the last, let's say that Fisba. Fisba is the company, the worldwide supplier of laser components, optical instrument, microsystems. They can make all the way from optics, all the way to laser diode systems. So anything that you need, Fisba is the right partner. It's one of the most trusted optical manufacturers that we have in EPIC, one of the most trusted optical manufacturers we have in the world. I try to be as fast as possible because now I give the floor to the smartest and most fun person in every room, Francesca Moglia. Francesca, what's in the menu this afternoon?
Thank you, Jose. Thank you for the introduction, also the sponsor of today. So today we have 8 speakers. So, and we will cover, as usual, the full value chain. And as we usually say, we want to see it in another way. We like to see it in groups like this. So very clear to us. So beam shaping means, and also pulse shaping means that we need instrumentation. And so that's why we have here in the room Optogama, Cailabs, MWTechnologies, and QIOVA that we can really discuss about the technology itself. Then, of course, beam and pulse shaping, you need optics. So that's why we have so many interested today in from the laser optics side. And so we have, for example, PowerPhotonic, Optoman, Asphericon, Oplatech, HoloOr, and then, of course, all the family of the micro-optics manufacturer that are also partially represented here, including our European funded project, Fabulous. Then other, of course, that need the system themselves, they have to integrate it. So they are our end user in this case for this meeting today. So for example, we have the workshop of photonics, so that for especially glass cutting, they are really famous, and we will have a talk today. Then we have all those that have fiber laser system like FIBO, but then as we heard already, space and defense instrumentation is also a lot of beam shaping, so PLX. Then we have laser machining. Of course, it's really laser machines need special optics, which beam shape we need. And so there is Lazea and Ilas also here presenting and as a present. And then we have, of course, also all the users from medical side, including Arisium and MedFab, that is our another EU funded initiative that we are also partner with. And then MIRFAB for sensor and spectrometers, of course, is important there, pulp shaping as well, and beam shaping. And surface structuring, of course, with the laser scanner and beam shaping is important for LAMPAS and other European funded initiatives of ours. And then of course, they also need laser diode manufacturer wants also, and laser components guys want to know how which kind of optics they can have in the let's say in the drawer. So that's why we are here, so that tomorrow their drawers are full. And so we have here, for example, Focuslight and monochrome for high power, but also our 2 pilot lines, also EU-funded initiatives like JEPIX for indium phosphide PICs and the packaging assembly of PICs-up that, of course, have to take care also of beam shaping. Then laser components is also, of course, so the main partners we have here are from Kyo Optics, Amamatsu, and EO Edmond Optics, Excelitas, and Fisba, as we said, from fibers to lenses to everything that we might need for beam shaping. And then, of course, the R&D. Without the R&D, we are nowhere. So that's why we have also all this research center, mostly in EPIC members. So we have like University of Birmingham, AMEN, Hyers, CSEM, some of the Fraunhofer institutes, Joanneum, and then there's at Centrum Hannover, also one of the last acquirings from EPIC and VUB, and also design software and of course, forgot it, vertical integrated laser solution, Coherent, of course, and other users of beam shape. But now, I guess it's best if we go back to our speakers, and I give the word back to Jose first.
We are broadcasting this meeting in YouTube, so for the YouTube universe, all of you, this is very important. We can connect you with any of the participants today. So for example, if you want to know who is that person from Laser Centrum Hanover asking all these smart questions, I will tell you it's Lars Jensen, and I will introduce you to him so you make all the right connections. Last but not least, thank you once again, all our sponsors, and also would like today to thank my team. Fantastic. We are working from Monday to Sunday, from Monday to down, non-stop, because we love so much the European industry. Many of you keep asking, what can I do to help you? Well, you can keep me awake. I am this energy level because I drink a lot of coffee. If you want to buy us a coffee, www.buymeacoffee.com /Epic Photonics. That's all you have to do if you want to buy us a coffee. We will share the proceeds with all the epic stuff, and we'll drink a lot of coffee to keep us energized. And that's all we have to do. We go to the floor and we go to Portugal. Miguel Melo is the CEO of one of the most innovative fiber laser companies that we have in EPIC. Miguel, thank you very much for joining this afternoon. Tell us how the rest of the supply chain can help you, and how you can help the rest of them. The floor and the attention is yours. Obrigado.
Okay, thank you very much, Jose, and congratulations for these very nice meetings. They are really well organized, I think, and quite useful, quite objective and quite useful, to be honest. So can you see my screen already?
Yes.
Okay. So I'll just Okay, so let's go. Again, good afternoon to everyone. So we are MWTechnologies, a company based in Portugal, and I'm presenting something related to pulse shaping and the ability we have to control not only the pulses, but also the amplification that goes after in the fiber lasers that we built. So we consider to have really truly agile fiber lasers with very high flexibility in terms of operation, either pulse shaping, frequency, and other things. So just an overview on our product portfolio. In the bottom, we have small drivers that actually are the base for our controls in terms of pulse shaping, including also arbitrary waveform generators that are included in the lasers, but that are also sold separately. Then we go through amplifiers, optical fiber amplifiers, and broadband and narrowband IC sources. And we end up with the pulsed fiber laser systems that I will detail more. So these are the three types of platforms that we can offer, and they are mainly working at 1064, 1550 nanometers, and the highest power we can go is around 20 watts of average power, 15 kilowatts of peak power, and the pulse width can be adjusted or shaped on the fly in real time, and you can also change the frequency from single shots up to 1 megahertz. So all the controllability, safety issues related to the fiber amplification is handled inside of the laser automatically. Which means that you can really make any kind of pulse, even if it's just a single pulse, square, typical pulses, or shaped pulses for some specific materials processing, or even if you want to amplify even more through a fiber, the laser we have, you can pre-shape it the other way around to avoid the saturation of the amplifiers. Or you can also have what we call the multiple pulsing schemes or pulse burst configuration, from where you can combine multiple pulses, either with the same width or different widths in different sequences, bursts, or amplitude. So this is also very interesting, and we can sell this as a product with low power, which is basically a laser diode that is directly modulated by our control electronics. But then if you want to have higher power, you need to amplify in the fiber. So that's the principle of our fiber lasers. And for that, we have developed a proprietary gain control model that automatically adjusts the energy and the peak power independently of the pulse shape, pulse duration, frequency, or even when you want to work on gating modes. So this is quite powerful if we join both together. And this means that in practice, you can have a full range of operation. You can start with very high frequency, 1 megahertz, 2 megahertz. In some cases, you can also offer that, and go down to single shots. And this can be done by the user, by the scanner, while you are scribing something, and the laser will automatically adjust so that the peak power and energy is kept constant, really, to single shots. Or even if you open, so if you gate it on and off, independently of the difference in time of the bursts, we always have peak equalization from the first to the last pulse within the burst. So just a small reference to this type of multiple pulses, because we truly believe that this can bring some benefits to some applications. And we have observed that although we only work in nanosecond regimes, some types of combinations can reduce a lot the thermal side effects when you are processing material, which means that in some cases this can be even equivalent to picosecond lasers. Some examples, just for you to have an idea very quickly. This shows several colors, and the only thing you do is just play around with the multiple flexibility we have in terms of pulse shape or frequencies. And you can pattern different colors in the same material just by changing pulse width or frequency and you can obtain a palette of colors in the same material. And this can be done in several materials. This is stainless steel, so you can scribe aluminum, you can get in silicon, and so many things. So just to finalize, because I know I'm reaching the time, I want to give the floor to others, as Jose says. So in summary, what we offer, so we offer a really flexible and unique tool. So you can see our laser as a tool for processing different types of materials or even new materials from where you don't even know how to start, which type of pulse you need, which type of frequency you need to process it correctly and to avoid the Haas effects. So, and you can optimize your process using our flexible laser. So this also allows this possibility of just changing the frequency on the fly while you are, for example, inscribing contours or corners, and in order to compensate the acceleration or deceleration of the scanner, you can simply change the rep rate of the laser because the energy will be kept constant automatically. We believe this is quite valuable also in terms of technology for other laser manufacturers that address mainly the materials processing market in this case, but there are other markets that we also explore and can be very useful, like medical and defense. And basically what we look for, so we look people that want to use our laser, either integrators or users that can take advantage of the benefits of these products. But at the same time, we also collaborate with other laser manufacturers, and we are open to collaborations in order to use part of the technology that we have and make them available to others if they want. So thank you very much.
Thank you very much, Miguel, for your talk. Now yeah, perfect. I'm unshare the screen. Thank you very much. So you perfectly already have the slide, the epic slide. So it's very good that you had it. I just didn't maybe understood if the pulse speakers, are you doing them on your own, or is maybe something that is on your wish list?
In terms of what? Of pulse?
For example, in the burst case, if you have acousto-optical modulators, or you have other things that you develop yourself, or if you have other system taken from outside.
No, this is much cheaper than using acousto-optic modulators, for example. So what we do is a really direct modulation of the seed laser. So we don't use acousto-optic modulators, nor we use pulse speakers in this case. So we just open or close the gates when we want a train of pulses. And to define the pulse shape of each individual pulse, or even the multi-pulsing, it's a direct modulation of the seed source, which is normally a semiconductor laser diode. So it's purely basically electronics acting directly in the laser diode.
I see. Okay, very clear. So do we have questions in the room? Otherwise, I know, yes?
Yeah, live from Dresden. Okay, Miguel, thanks for this very interesting talk. And maybe I remember you on Photonics West, or I see some results on other presentations. And worst case, 20 watt, infrared, 5 nanosecond, 1 megahertz. What does it mean, change in the fly?
It means that you can sweep the frequency down to single shots.
Yeah.
And it means that you can change the pulse width as well independently at any time. And the laser will adjust the gain so that the peak power or energy remains at the level that you have selected.
You have any idea about the coherence length of your laser sources?
We have, so I think you are probably, so they are not coherent. So actually we don't want them to be very highly coherent because of SPS effects that can trigger within the fiber. So we make it safe enough in order not to trigger SPS, for example.
What a pity. I need a coherent length from some millimeters for a daily application.
Okay.
You know something about our laser interference patterning? And maybe we found some new applications for your laser sources, if you like.
Yes. So you were talking about the worst case, which is the highest power, which is the highest peak power within the fiber. We mainly work with silica fibers. And from there, we have some nonlinear limitations, but we are very happy to and glad to talk to you directly and to understand better what you need and what you'd like to have, and try to see if we can offer you a solution.
Okay, thank you very much, Miguel.
You are welcome. Thank you.
This sounds already like a plan, so please catch up later on, and then you can discuss this, and maybe Miguel can also push a bit his specs towards towards Dresden. Thanks a lot. So are there other questions in the room? Because if it's not the case, maybe I can ask Jose already to introduce himself, not Jose Pozo, but our Jose from LASEA. Thank you very much for being here. So you're a system integrators. What do you want to tell? Why are you attending here, and what would you expect from today? You are muted. Huh? Now not anymore.
Is it mute?
No, yeah,
Well,
we hear you.
Okay, first of all, thank you very much for your kind invitation to be here. It's a very interesting meeting, and it's a subject that interests me also since a very long time ago as an optician, working in integrations of industrial laser machines, of course. And as many of you may know, LASEA is specialized in ultra-short pulsing applications, but not only. So we have as well applications that ask for other pulse duration and more affordable technologies as this one. So we find a strong potential of this technology in particular in relation to the control that we can do for the interaction thanks to the temporal control on the pulses. This is something that I think has not been researched much, and that could optimize a lot many applications. So being aware of the, in particular, these type of lasers, but other products that I will listen very carefully, is something very interesting for a machine integrator as us.
Very good. Thanks a lot. Thanks a lot for the explanation and for introduction of yourself. Hopefully you can hear already something today about it, or you can offline also follow up to someone that is here, or maybe on YouTube we will see, and we can comment also later on. So now is maybe time to stick to the agenda, and we can go directly to Lithuania, right? To Antanas, workshop of photonics. Welcome today here. It's really nice that we met the last time on an exhibition, and now we only meet here online, but yeah, better than nothing. Okay. Thank you very much. So the floor is yours, Antanas.
Okay. First of all, I would like to say my big thanks to EPIC, Jose, Francesca, and Helena for this splendid opportunity to meet friends and colleagues, and to present what we can do for this community. So now I'll try to share my screen. I hope it is already.
Not yet. You need to press the share screen button at the bottom of the window.
Like you did before, the green one below.
Good, would be good if I could to find it.
It just appears if you go down with the cursor.
Yeah.
Yes, it's coming, something. Let's see if the right screen. If you go to presentation mode. Yes, great, Antanas, the floor is yours.
With your help, I'll manage.
Yeah, of course.
Okay, just a brief self-introduction. In Workshop of Photonics, we are a company of 30 plus people, and we are working with micro machining by means of femtosecond lasers. Francesca put us on the shelf with where system integrators are, but we are not only system integrators for glass cutting, but we develop the technologies and processes for other integrators. And by doing this, we develop some special tricks and things to be implemented into these processes. And again, by doing this, we came to development and manufacturing of quite specific optical elements for beam shaping, which I want to share with you. So, what it is? These are space variant retarders, which are used for beam shaping. What is space variant retarder? Standard wave plate is a piece of birefringent crystal, which fast axis constant direction, and the retardance is also constant. In space variant retarder, we put both fast axis and retardance as the functions of the space inside of the element. How we do this? You can see this long shape on the right side. It is the path which is created by a femtosecond pulse if you direct it into fused silica, and if you know how this pulse should look like. And these pulses make self-organized nanostructures, like on the very right-hand side. Where is my mouse? Here. And these structures are perpendicular to the vector of polarization of the light you put into this fused silica. And this structure works as a very small, tiny wave plate, which you can turn it, and which it means that you can turn polarization of the light which goes behind of your element. And if you know how to inscript your structures in fused silica, if you control fast axis, you can build very famous elements for beam shaping. Here you can see example of very well known our standard product, which we call S-plate. This is a converter which converts Gaussian beam with linear polarization into optical vortex with radial or axial polarization, which you can use in very many ways. But along with that, you can make very different masks, like in this example. You can make this cubic mask for building airy beams, and I'm not sure if you can see it very well. On the very right bottom side of the slide, you can see that what this airy beam can do in your glass. So, what when developing these technologies, we work mostly with transparent materials. And it means that we are able to use non-diffracting beams, which can be focused in the volume of transparent material. And one of the most popular non-diffracting beam is bezel beam. You can make it with simple phase mask by space light manager with SLM, and you can get quite good shape of bezel beam. You, in theory, can use for fabrication, but the disaster of SLMs is that they cannot withstand the high energies. So you can use bezel beam from SLM for multiphoton polymerization or other applications that kind, but for cutting, drilling, and so on, you cannot not use it. So what we do, we use not simple phase, but geometric phase, which is called Pancharantan-Berry phase masks. For making this mask, we have to arrange these nanostructures I showed in the previous slide in a specific manner. We have to calculate before. Some people call it computer designed holograms, but it's not really hologram. But in any case, if you make this asphericon emulation in the Pancharantam berry phase, you can get a mask which builds either positive or negative asphericon emulation, depending on polarization of the light you send to the mask. And if you use linear polarization, you may have both negative and positive asphericons simultaneously. Another important thing is that you can you have an opportunity to achieve stepwise longitudinal profile, meaning that your response of your material will be uniform along the beam you send into material, unlike standard Bessel beam you make. So I mentioned high energies for fabrication. So first, one important thing is that you can use it in very well shape, because Sabrina from asphericon will confirm that for refractive asphericon, it is very important to have sharp tip, because if the tip is round, you have some stegosaur shaped distribution along that axis. In our case, this uncertainty on the tip is less than 20 micron, is down to 4 micron. So, which means that actually we can build the distribution of practically as perfect axis. So another case for beam shaping is the XY shaped non-diffracting beams. A simple case, if you take the mask of asphericon and you shift the halves a little bit from each other, you may get beam-like form of your section of your Bessel needle. So it means that you can more efficiently make cuts in your transparent material if you want to do cutting or drilling. If you go to tricky cases, we develop some for very specific applications. We develop interesting things like in the bottom side, which is set of 8 Bessel beams, like you see in the 3D measured intensity. But for that case, you have to inscript the mask, which changes your amplitude and phase of your beam. But again, which is quite important, you have stepwise super Gaussian distribution along z-axis. So, summarizing, I can tell that in the time we develop applications for others, we develop very specific kinds of optical elements. We willingly share with our customers and with anyone in the EPI community. So this is my main message, that if you know what you want, we may help you with the element. If you know what you want to achieve in the material, we can start from developing the process for you, which may or may not include developing specific optical element, which will help you to achieve your task. So that's it, and thank you. I'm ready for questions.
Acho, Antanas, like usual, every time that we put the workshop of photonics on stage, we get a lot of questions. The first question is coming all the way from Israel. Natan from HoloOr. Beautiful, beautiful DOE demo just next to you, by the way. I think we have a problem with your audio system. We cannot hear you at the moment. I think we'll come back to you. We're going to go to the beautiful, beautiful city of Aachen. I think we have another request for intervening from Fraunhofer ILT. George, thank you very much for joining. Tell us what you're doing in this meeting. Maybe you have something to collaborate with Antanas. I think we have you muted. You need to unmute yourself. Yes.
Okay, great. Thank you very much. And thank you for your interesting talk, Antanas. Me, as a member of the Fraunhofer ILT in Aachen, we are developing laser processes and especially high power laser processes. So for us, always the big question is, are there any limitations in terms of the size of the elements that you can offer and the beam power that these elements can handle?
Yes, of course, there are some limitations. We usually limit ourselves with 15 millimeters in diameter because it takes quite a long time to fabricate such elements. And obviously the possibility of error increases. And you might fabricate 5 days, and the end of fourth day you make some drop in your power or some water cooling mismatch, and your element is out. So actually we make it, standard element is 6 millimeters, and we make it up to 15 millimeters. And to power, I went it very, very quickly through. We made damage threshold measurements, and we got for nanosecond 63 joule per square centimeter and 2 joule per square centimeter for 200 femtoseconds. So it's practically same limits as pure fused silicon, a little bit lower, but not significantly.
So George, why did you join this meeting? What can you do for them? What can they do for you?
Okay, thank you very much. In Aachen, we are, like I said, we are doing research and development for high power laser systems, but not just the systems, but also the application of the systems. So what we can do for you is we can do experiments. If you have a crazy idea, maybe if something can be processed with a laser, we've got a big park of machinery. We can easily and quick do a test for you if your application is doable. And if you like, we can develop the machinery as well. And what we are certainly good at are high laser powers. We're good at multi-beam processes, and we are good at beam shaping. Obviously.
Fantastic. Thank you very much for joining today. We go back to Israel. I think Natan solved the problem. Yes.
Jose, do you hear me?
Loud and clear.
Thank you. So sorry for wasting your very nice introduction earlier. My name is Natan from HoloOr. We are a diffractive optics manufacturer and designer. And I have a few questions to Antanas. So basically, we also make diffractive optics, but not polarization sensitive. I was wondering, for your method of sort of sub-wavelength grating, which makes a birefringence that's controlled, what is the reasonable modulation distance? I mean, usually you need to change this adiabatically, so you can't get a lot of contrast in phase. Let's say in terms of angles, what is the angle of an axicon, or typical axicon you make?
You found another weak point in our systems. So actually, the axicon we can build in this way. The minimum apex angle is 176.
Okay.
We don't make it smaller because it needs two small structures which are below limit.
Okay, thank you. And another question: does the laser have to be linearly or circularly polarized? I guess it is. It cannot be randomly polarized.
It depends which element you would like to use.
Okay.
So some elements can work only on the circular polarization, and some elements work differently on each polarization you want.
Okay, thank you very much.
Antanas, from the YouTube universe, your presentation generated a lot of debate. I'm not surprised. Have a couple of questions. The first one is from Simon Ferrer. Simon used to work at NIT in France, but now he's looking for new opportunities. I'm sure he has a lot of them. But he's asking, is it possible to replace fused silica by another material like germanium, sapphire, silicon selenide, or any other higher wavelengths?
We tested many materials, and the only material which was comparable to fused silica in terms of organization of structures was ultra low expansion glass. But the efficiency was much poorer. So fused silica is practically only material which is suitable for these structures.
Fantastic. I go to the capital optics in Europe, Jena. I go to Genoptic to get the question from Klaus Stolberg. Which accuracy is required for the XY alignment of the element?
Again, it depends on element, but if you want to use our flat asphericon, we call it, it is actually simple visualization with visualizer of a standard beam. It is enough. It is not microns. It is tens of microns.
Fantastic, Antanas. I'm going to go now to Neuchâtel, to SUS Micro Optics. Wilfred, thank you very much for joining today. How are you doing?
Good, thank you very much, Jose.
I think you have something to comment on fused silica, right?
Yes. So for fused silica, actually, we're doing now very small feature sizes now, about 200 to 300 nanometers. You can etch those 1 micrometer deep. I don't know if this could help you. So that could be for diffractive optics. And we have a very high precision. So I don't know if this can help you. So this was originally developed for the AR area, for augmented reality, these very fine gratings on diffractive optics. So that might be helpful here as well.
I think there is something that you need to discuss, and I will introduce the two of you, which is something I love doing, and you know that. I'm going to go to Hanover now. I'm going to go to Lars. Lars, do you have a question?
Yes, thank you. Nice presentation. With fused silica, of course, you're very flexible in wavelengths and also go into shorter wavelengths. What are your limitations towards the lower end of the spectrum? Do you use those optics for visible or even UV?
I can tell you about transmission without anti-reflection coating for third harmonics, 343 nanometers. We have efficiency achieved 85%. And for second harmonics, 92. So if you add 10% with anti-reflection optics, it is quite okay.
What an amazing Q&A. I think it's time to continue. It's time to go to New York. It's time to go to PLX. Thank you, Michelle, for joining us today. What can we do for you? What can you do for us? The floor and the attention of everyone is yours.
Sure. Thank you so much for introducing me. I'm going to start sharing my screen. 1 second here. Okay, great. Can you guys see me?
Crystal clear.
All right, great. So, hello, I'm Michelle Hyers, the Director of Engineering from PLX, and today I'm going to be talking to you about transforming optical structure technology through innovative system integration. So basically what we do here at PLX, so hello from New York, is manipulate light. So this is really relevant to this talk today regarding laser beam and pulse shaping. So anything that involves manipulation of light, such as sub-arc sunken beam delivery, targeting, bore sighting, beam steering, folding, laser systems, interferometry. So we have some of the examples here. So we're really the pioneers in retroreflector technology. So if you can see in the bottom left here, that's kind of where our history had started in making these retroreflector systems. And that was just kind of the intro into this series of different applications. So We have all these other systems, lateral transfer hollow retroreflectors. We have this example here and the periscope example. But really the heart of what we do, a lot of this custom OEM application and integration. So really a solutions provider. So I thought this talk would be great today to really integrate some of these applications in beam and pulse shaping into the platform of what we do. So in terms of just getting to know and understanding what we do at PLX, we are working at all these different levels here, from the assembly levels, making these optical assemblies, all the way up to subsystem and system integration. So that's really the power of our technology, to really go through all these levels. And the idea is always to kind of get to that integration level, is where we can kind of produce the most benefit for your systems. And then what, I'm going to mention this a little bit more later, but what we're really looking for in terms of EPIC is really working with key partners in this area. So really finding interesting applications and coming up with solutions for the market together, utilizing a lot of our expertise and what we are already doing, and really pushing what we can do. So in-house, we really work on engineering design. We have our team of engineers, and we go through a whole process to really come up with and design optical assemblies that perform extremely well. Really what we're best known for in our expertise is making these systems that work in really robust conditions in terms of vibration, shock, thermal systems. So we do an FEA analysis. We do a lot of environmental testing to really prove out those systems. And then, we also are doing that fabrication, precision assembly, all the testing, in-house coding. And that gives us the ability to really control what we can do and really push the boundaries of that as well. So in regards to this talks today, there's a lot of different methods and implementations for beam and pulse shaping. So what I wanted to kind of talk to you guys, one of the things that we really work on in our main technology, I'm going to talk about and introduce shortly, is monolithic optical structures, which we call the MOST. So there's all these different elements, you guys, some of the talks already went over a little bit, is different ways to basically manipulate the beam or pulses. And a lot of those can involve many different methods and elements that can be integrated into a monolithic structure. So if you take something like a system, one portion of this may be a beam shaping or pulse shaping unit, but there's also ability to really think about this at a higher level in terms of integration, where that element could be, or that system could be part of a larger system. And that is the benefit of a monolithic structure. We can put all of those elements into one highly accurate assembly. And so you can really think about these optical structures and systems on a different level, where you might not have to have all these different separate portions, but you can really kind of have an all-in-one solution. And these monolithic structures are really beneficial in terms of thermal capabilities, vibration environments. So it's not really limited to some of the conventional optical system approaches. So with that, if you think about a monolithic style approach to this kind of all-in-one structure, you can really get high accuracy. So PLX specifically, we can go down to sub-arc second beam deviation, and that's the overall assembly level beam deviation. And we also are very strong in what we call invariant optics. So I mentioned the retroreflector example as an example, but really expanding on that, you can also carry those into the monolithic optics as well. And it's highly configurable. So anything that, any kind of systems that you can think of, we can really combine at the assembly level. So there's really not a limitation. That's just the technology is really just the structure and the ability to put these things into the assembly, but there's no limitation of what you can put together. And the stability is really, again, a lot of our systems, we call them are just happen to be in a lot of the military defense markets. So these battlefield ready. So things that if you're transferring that over to a lab or scientific approach, any vibrations and laser power and all these issues you might think of are really performing well in the most extreme environments. So it's usually not a concern. It's actually a high stability system. Component integration. So we're talking about all those different elements. And I think you guys went over some of those. These you might have in those systems, you might for beam impulse shaping, you might have reflector, like mirror elements, you might have lenses, you might have diffractive elements, you could have filters, polarizers, all these different sorts of different methods to get to an overall optical system. And in that, you end up with a very complete enclosed design. You don't have to worry about alignment issues and stability. Things aren't going to be moving and changing for those elements. And in terms of, you know, you still might have some optics or elements that might need to move or modulate. And when you get into things like that, another thing I wanted to bring up is that our ability for PLX to really integrate with MEMS. So some of these systems in this application could be MEMS driven. And so we have actually done and collaborated with partners in this field to really provide, you know, these are examples of basically other MEMS mirrors and using like our retroreflector technology, but integrating in a deformable actuated system. And this is an example that we worked on for actually this free space optics to provide optical communication. So this is just, I want to just show this as another example. Scale for us is also very flexible in terms of going down to even this MEMS level up to even very large systems. So really PLX, we're really focusing, especially this past year, really pushing the limits on what we can do in innovation and building up our technology. So I had mentioned this before. So this is our this is our monolithic optical structure technology. And I'm going to show you guys just a quick video, but I just want to show here, you know, this is an example here. This larger picture is an interferometry product that basically we offer. But if you look at all the photos below, they're all different configurations using the same technology, but the applications are vastly different. And so there's a lot of flexibility in that and what we can do. So we're really looking for those very interesting, exciting applications, and we're really looking forward to working and collaborating with you guys. So let me show you guys a short video. You guys hear that okay? So with the most that was just interesting in the video is really going over the ability to take all these different elements and specifically for this application, whatever elements you need, if it's diffractive elements, if it's a series of different multiple filters or anything you can really you can put into the system and really build it into your overall optical system. So there's no really limit of what we can do in terms of the type or number of elements we can put in here. And you really get this compact, you know, we call this like the sandwich-like structure. It gives you this this plug and play sort of ability to take your optical system and really put this one element in to replace multiple different systems. So with this, you get the optical stability that we talked about and the shock and vibration resistance. You get this extremely high accuracy. You don't have to worry about all these different elements and components getting loose or moving around in different conditions. So you get this kind of permanent alignment that's very powerful. And in terms of what we can do all different types of materials. These just happen to be some of the examples shown. Let's say we're fused silica or low expansion glasses, but we can do metals, ceramics, and we have before. And a lot of this is just depending on the CTE. We try to, all these systems are athermally designed, so we try to match CTE. But this allows us to have really strong accuracy even over a large thermal excursion. So with PLX, we really take all of these capabilities. So, you know, the heart of what we started out historically is just doing these hollow retroreflectors. That's one of our core components here, and our monolithic structures is really built onto that. We also do a lot in lightweight optics. So whether it's the optical and mechanical or both systems, really optimized for these specific applications. And then invariant optics, that's also another powerful technology of what we do. And all those come down to, again, the system integration. So we really like to get in early into your guys' applications, because we really can have such an advantage for you at just the initial level, assembly level, but also this integration level. So just to give you an idea, just these are some of the sizes and metrics of what we've done before, but we're always pushing these boundaries. This is just a guideline, a starting point. So beam deviations on an overall system down to 0.2 arc seconds. In terms of sizing, you know, I mentioned the optomems. In retroreflectors, we can go down to 2 millimeters. It's just a standard size that we offer, so we can push down if we need something customized. And just some of the scale of things, you know, on the large side of things, going up to, you know, meter level is not an issue as well. So we're really not limited in size. In environmental conditions, this is where we really shine in terms of providing the best performance, keeping that performance in adverse environments. So whether it be shock, vibration, temperature, these are kind of just, again, guidelines of what we can do, and we've produced before. So in terms of applications, we have, you know, a lot of experience in multiple markets, defense, aerospace, and commercial, and we've done some of these applications in terms of laser beam and pulse shaping in these industries, and we're looking to kind of expand on what we can do and who we can partner with. So we have these examples on the left-hand side of some of them, and I'll show you some more kind of examples to see what we can do. So this is just the image really showing all the different applications and variations of what I just talked about. So you can really expand on some of these. Some of these on here are the monolithic structures. Some are the retroreflectors. On the bottom, you can see a retroreflector array that looks like that honeycomb structure. We have ones that are basically rotary devices. We have pentaprisms, pentamirrors. We have autocollimators. There's really just such a vast amount of solutions. So we are really providing, you guys have your application, you give us the details. So you give us the details of what you want to achieve, and we can design, fabricate, and test, and come up with the high precision assembly that really meets your needs. So it doesn't matter if there's very tight, high precision, vibration, shock, all of those is exactly what we are the best and excel at. So that is PLX.
Thank you very much, Michelle, for your contribution. Yes, you can unshare. Very good.
Thank you.
Thanks a lot. So it was a great overview of what you can do and what system integrators should contact you very early, but there's something missing. So what can they do for you? So not only the integrators, but maybe some supplier. Do you have something on your wish list that you would like to talk with this audience?
Yeah, I think I mentioned on somewhat of just, we're looking always for new partners. So in terms of things like, for instance, in our monolithic structure is, you know, if there's an interesting component or something to combine with our technology, I think that there's a lot of power in that. So we can kind of have a combined approach to bring to the market as well. So I think through some of these epic talks we've actually started and helped. It's really powerful to help engage on that level, to really find true partners to expand both of your technologies together. So if anybody has any, it doesn't always have to be just a customer. We're looking just to kind of see what possibilities are out there.
Okay, so, and is there someone who wants already to propose a deal with Michelle here? So, now there's Natan. There is a fight, they are fighting. Please, you can go ahead.
But nice talk. And on one of your slides, I have seen the SLM. It's SLM. It's your own product, the SLM, or is it SLM from Hamamatsu or other commercial available product?
Oh, so on which one? Sorry, I missed that.
On one of your slides, I'm not sure which one. You have a design, optical design with a SLM modulator.
Oh, okay, yeah, I think it was like, you mean the slide on the beam shaping?
Yeah.
Yeah, I was just using that as an example of just an existing system.
It's a system from a commercial partner.
Yes.
And you know how much energy can I send through the SLM? Maybe some microjoules or millijoules, or is your optical design only designed for telecommunication?
On our MEMS system?
MEMS and also the SLM system.
Yeah, I mean, we've done vast and different applications. So we're usually getting our kind of business structure. We're getting kind of the OEM, requirements, and we're building to whatever those requirements are. So there's all different, whether it was the MEMS or other optical systems, those requirements come to us, and we can build whatever system you need. So if you have specific,
it's also working with picosecond and some microjoules, or maybe I destroy your optical design.
No, I think, I mean, we can talk about different possibilities. So I think we've never kind of stopped at a solution that we couldn't try to tackle. So yeah, if we want to talk further about it, I think we've done so many applications. So I think it's a possibility.
Up to now, I didn't found any SLM systems who are worked with for laser microfabrication. I always destroy SLMs. I'm sure I always do this with your SLMs.
Okay. Well, yeah, no, I mean, I think we can figure out something.
Okay, thank you very much.
So, and then I guess it's time for Natan, right? You were speaking at the same time. Yeah.
Just a short question. Are you interested in Athermat diffractives? I mean, I saw that you said you use diffractives. Yes. Do you use Athermat lenses that are diffractive based?
Yeah, I mean, so in that monolithic structure, we can integrate different types of diffractive elements. Athermal would be excellent for us to really merge with our technology. So providing, if you want to partner in that sort of realm, that would be great for us to provide, more, we have kind of existing some products that we offer as a kind of standard, but like I said, most of our technology and our business model is out of these kind of custom applications. So if we can kind of merge those two and come up with some applications directly for the market, that's perfect for what we're looking for.
Okay, so basically you're not looking for suppliers of Athermats or diffractives. But...
Oh, no. Yeah, no, I'm saying we're definitely interested in that as well, because we might have the, as we have that application come into us, we need to supply the end solution. So there's both sides are feasible, whether you guys come to us or we kind of come to you. It's a partnership.
Also, do you get inquiries for large line systems, large narrow line systems, like for high power lasers, or usually it's telecom?
I guess it's a mix. It depends on the application. So a lot of our applications tend to be more the defense military market. But that's not, that's just a kind of majority, but we're really doing a lot more recently and pushing to partner in more of the commercial space.
Sure. Thank you, Michelle. We'll be in touch, I guess.
Very good. So Michelle, you never talk about coatings. Is there something that is interesting for you? So are you looking for some demanding coatings? So demanding so for high power, for example?
Yeah, so we have our partners we work with in terms of coatings. Yeah, so I think there's always in terms of coatings, there's always a need to try to push that as well. So yeah, if there's anybody to connect with us on that, then we're also always interested as well.
Then there is some in the room with whom we start first. Maybe with Remigius. just because on my Zoom is close to me. So from Optoman, I Remigius.
Right, I'll try to unmute myself. So I am Remigius from Optoman. We do IBS coded optics. I actually have a couple of questions for you. Do you do those assemblies for ultra-fast laser applications? Is this something you can handle and deliver to your customers?
Sorry, deliver
ultra-fast laser systems, femtosecond,
Oh.
picosecond stuff. So mainly femtosecond. That would be a concern because of group delay dispersion compensation. You have many surfaces there in your systems, so you have to be aware of that kind of stuff. So.
Yeah, no, we've done work in that area before. So yeah, I mean, we've done many. I didn't show all the applications. A lot of stuff we're doing is custom OEM, so I can't really show all the different applications. But we've worked in that area before. So yeah, I think that would be fine. It just, yeah, there is different considerations and requirements for different systems, and whether we have to have different concerns or design the system differently or different coding requirements. We just kind of design accordingly.
Okay, so this is this topic is really interesting. I'm not sure if you have these capabilities in house, because you mentioned that you have a coding job shop in your factory. Yeah. So
yeah, it depends on the coding and you know, whether we can kind of do stuff in our capabilities or work with key partners depending on the application, the requirements, etc. So I think offline we already I think talking to you a little bit. I don't know about kind of connecting, I think from another Epic meeting. So I think that would be great.
Yeah, Vitos was bragging that he's in contact with you. So
when it comes to hardened coatings, it doesn't get any better than Optoman. So sorry, Michelle, but you're not working with the best. You're not working with them. I have a question from the YouTube universe. I go all the way to Freiburg. I'm making a lot of new friends during these online technology meetings. I connected with Andreas Brand, who is the laser expert in Fraunhofer ISE. He has a question and a comment. The comment is the accuracy of the monolithic structure in itself is nice. However, the input beam positioning and stability is often equally important as the overall system's stability. And his question is, do you offer a solution that takes into account systems and beam stabilization built in, or even agnostic to the operator to beam position angle instabilities?
I think one of the things I didn't really go over too much in this talk, because I was focusing on the monolith, is a lot of our systems are actually invariant systems. So where, you know, like the retroreflector example, where you can basically not so sensitive in terms of the laser, the input beam. So a lot of the power of those invariant systems is not that sensitivity of the input, the positioning. So we have an example we just were at when we were at Photonics West, where we had our invariant monolithic system, and we kind of just take it, you know, this high precision system, and really just whatever the beam position, and just drop it into the system literally, and everything is already repositioned and aligned. So that is another layer of what we kind of the benefit of our systems and what we can do. So if you have an invariant system, that kind of negates that sort of issue or concern.
Fraunhofer ISE is a great company to interact with the solar industry. So I'm going to make the introduction of the two of you, and I go back to Francesca.
Thanks a lot, Jose. So now I guess it was a hot Q&A session, but maybe we stick to the plan and we go to the next speaker. So now it's time for Tadas, from the CEO of Optogama. So Tadas, are you ready? Are you ready to roll? Yeah, then the floor is yours.
Okay. Thank you very much for introduction, and thank you, Epic, for this opportunity to present our products. I'll try to share my screen. Yeah, so today I will talk about the quite simple optical systems for beam delivery and beam shaping. And mostly what we do is free space optical elements based beam shaping devices to control laser beam diameter or divergence or intensity distribution, to control polarization or laser power control in your system. And mostly we deal with the high energy ultra fast laser manufacturers or integrators or machine builders. And we design custom beam delivery devices, as well as we have standard product portfolio for these tasks. And the issues that our customers mostly faces is a mostly complicated integration or poor beam pointing stability during the operation with the beam shaper or beam expander. As well, if you work with the high energy femtosecond lasers, you could face the laser damage threshold issues. And that's the case we can talk and we can start our cooperation. Moreover, we take care about the B-front distortion or astigmatism or the beam quality out of the beam delivery system. So what we do, so we do devices. I will present in the next slide what kind of the devices we have. But these beam expanders or beam shapers could be designed for your single laser line or dual band, like a first and second harmonic or few harmonics, or it could be broadband devices. We can cover the spectral range from UV, from fourth harmonic up to mid-IR, up to 2 microns. In the beam expanders or beam divergence compensators, we can ensure high beam pointing stability less to 0.1 milliradian. Our motorized or automated devices integrate controller inside, so you don't need any external controller. In the beam expanders, the lenses, 2 lenses moving simultaneously, and you will have no misfocus or ghost inside of your beam expander. Our devices integrate encoders to ensure absolute position of the lenses or of the other optical elements, or for example, rotating elements. All the elements are made of high damage threshold materials like fused silica. You don't need any homing or any preparation of your device. You can just plug in your power and you can start to work with. All the expanders or divergence compensators are tested in the lab for the beam pointing stability, for the magnification repeatability, and the wavefront distortion. So when you get your device, you can just install and work. It is quite simple, robust, reliable, and but if you need some complex solution, we can integrate some shapers inside. We can integrate aspheric, some conical optics, or multifocal beam. We can build some polarization wobbling or beam wobbling system for micro machining applications. And the products, what I am talking about is beam expanders. Here in the pictures, you can see motorized beam expanders. We have standard magnification 1 to 3 times, 1 to 8 times. We have high power dedicated motorized beam expander. It's a bit larger, but it also integrates controller inside. We have manually adjustable expanders, fixed expanders. We have laser power attenuators to control laser power. And as well, we have devices we call beam delivery devices. It integrates laser power attenuator and beam expander together. And from one device, you can control laser power, beam divergence, beam diameter, and you don't need any additional devices to do that. So it's a quite short introduction, and feel free to ask questions.
Thank you very much for a great presentation. A show as well to you. I love the companies in Vilnius. By the way, next year we have our annual general meeting in the capital of optics in the Central Europe, in Vilnius. Thank you very much for being with us. I think I want to give the floor to a few of your potential partners. I'm going to go to one of my favorite companies in the micro-optics world. I'm going to go to Limo. Dirk, thank you very much for joining this meeting. What do you think about the meeting so far? What does Limo do in this field, and what kind of cooperations, connections do you want to make after this?
Yeah, thank you, Jose. Thank you, EPIC team. It's a very great and very professional meeting again, and I'm happy to join the meeting. So What is LIMO doing? LIMO is a part of Focuslight, and we are shaping laser light, high power lasers, and change the intensity distribution and the spatial distribution to improve the process stability and process speed using lasers or several lasers together. So therefore, beam shaping is a hot topic in our company since 20 years. And therefore, we are always very open to address our questions to the community, because to stabilize a laser in time, in space, is the key to stabilize the processes. So therefore, we are always looking for partners, for suppliers that can stabilize the power and attenuate the power without changing mode geometry, intensity distribution, because that's the input that we need to stabilize and use our micro optics to bring the beam to the application in the right way.
Dirk, whenever you have the chance in any exhibition, you should stop by the booth of Optogama and see their demo on beam shaping. It's actually quite fascinating. Tadas, any challenge for the optics manufacturers in Europe?
So we are looking for the partners who want to integrate their free space components like a shaper into the motorized system. So we are looking for such partners to build together automated product that's integrate quite complex elements inside of such device. Yeah.
All right, there's something else I want to discuss, because in the YouTube universe, one of our members, IHB, Holger Bedersen, actually wondered, the companies who are manufacturing beam shaping instrumentation, are there any challenges with the housing of the product? How does Optogama deal with the housing?
So actually, we design all the optomechanics in-house, and our production is here in Vilnius. So we don't really face any issues at the moment. Maybe if you have some ideas for thermal systems, for shock and vibration resistant systems, we would be interested to discuss for fabrication of such optomechanics.
I will make an introduction, because definitely they can help you with that. The same question goes to Miguel Melo from MWTechnologies. How do you deal with the housing? Are you looking for potential partnerships on that topic?
The housing of the lasers itself?
Yes.
Yes, we deal with the housing of the lasers itself, yes.
If there is any challenges that you would like to open for the companies in EPIC that want to help you on this?
To the high power levels that we currently work with, so we do it internally. If we want to go probably to higher powers, where we need probably some more mechanical improvements due to some heat dissipation stuff that we need to do extra, maybe we will look for some partners.
Thank you very much, Miguel. I will make an I love doing this, by the way, making these introductions afterwards and making sure people follow up. And I'm seeing a lot of following ups. I would like to go to Munich. I would like to go to Coherent. Thank you very much for joining today. It is great to have Florian with us. Florian, you're muted. I think we need to unmute you. Yeah, let me get back to you. I think we have a IT little problem. We have a little IT little problem. So we go first to Cailabs. We go to Cain and we go to Cailabs because we want to learn how we can make any beam shape that is in our mind. And for that, there is no better company than our French EPIC members. Gwenn, thank you very much for being with us this afternoon. The floor and the attention of your potential partners, suppliers, and customers are yours.
Hi. Hi, Jose.
Hi.
So let me share my screen.
Yes.
And you will let me know if it's working well.
I see you crystal clear. Gwenn is always full of energies at this time of the afternoon. You will see.
Yeah. So which screen do you see?
I'm seeing the wrong one.
Okay. Never mind. We will manage. I had the same issue just before. You know what? I'm back in my company, meaning physically in my company, for the first day in 3 months. And my screen are reversed.
Ah, that's a pity. I think the people were messing with your screens while you were at home.
So are we good now?
We are still bad. We are still sharing the wrong screen.
Never mind. I try the last option I have. Should be good now.
Yes, it is. The floor is yours.
Okay, great. So thank you very much. Thank you for organizing that very nice meeting. One more nice meeting from EPIC. Very good for connecting, definitely. And My name is Gwenn. I'm working for Cailabs. And well, basically, we are fully in the topic of today because we are doing beam shaping. And I will today talk about what beam shaping can bring to laser material processing. I will have just a very short introduction about the company because we are a pretty young company and all of you may not know us yet. We are a French deep tech company and whatever we are doing is actually more or less based on our core technology, which is MPLC for multiplane light conversion. It's a very new way to think light propagation and it enables a lot of new things, as Jose did mention. And it has a lot of different applications. So we had a lot of good partnerships over the years, people who trusted us. But today we will just focus on one thing, it's material processing with lasers. So I will start, but what can we do with beam shaping for material processing? Well, basically, we are always focusing on two things. Either we want to improve the quality of the process, either we want to improve the yield of the process. And sometimes you actually want to improve both. So whenever you have a laser, which is in a factory or in a workshop processing goods, we are looking at that process and we try to improve it. So today I will just show you a few examples of processes which we have worked on last year. And then we will discuss about what are the possibilities of our systems. So the first example is laser beam welding. We did work on that with the Institut Maupertuis. And it was a really nice collaboration. We were doing actually a donut shape. And the idea of that donut shape was to improve the quality of the welding. The idea is that you reduce a lot the sputters when you are doing the welding, which you cannot see on the video because we don't have the gas flow on the welding. But the idea is to improve the quality with very high power laser. We did work up to 16 kilowatt with CW lasers. The second process which can be improved, for example, with beam shaping is glass cutting. We did work on that with LZH, our good friends from Germany. And in that case, we were doing Bessel beams. Bessel beams is a very nice example of improving at the same time the quality and the yield of the process. We improve the quality because our Bessel beams are of the highest quality possible. And the drills are really nice through the glass. And at the same time, because the beams are extremely stable, you manage to go through a scanner, and then you manage to really improve the yield of your process. The third process, which I will just shortly introduce, is engraving or decoating. We did work on that with Lasea. That was also a very nice collaboration, and we thank them for all the work we did together. The idea was sent to split beams, so you really look at improving the yield quite a lot. In that process, the process was done using less than 10% of the available power of the laser, and then when you split the beam by 9, you just improve the yield by a factor of 9. So that was really really nice, and at the same time, you manage to keep the good quality of the process. As you can see, actually, it's very homogeneous in between the different spots of the splitting. Just shortly, the last one, surface texturing. There are so many applications of surface texturing. Today, I will just talk about blackening. We did that with Alphanov last year. And in that case, we were doing a line top-hat for improving the yield of this process. So the idea was that it was a very high aspect ratio, and it was top-hat over the whole lens. And by doing that, you improve to increase the yield by a factor of 20 in that process. So all the three last processes, glass cutting, engraving, and surface texturing, were all done with femtosecond lasers. I have just these examples, but I just want to say that we are looking at other processes, of course, like laser cutting with high power laser, additive manufacturing, or all microprocessing applications such as drilling, for example. Then what do we offer for material processing? Well, basically, we have 3 product lines, and each of them are really focused on being compatible with all the industry constraints. The first one is Canada HP, is for any kind of complex shape with high power CW lasers. And I would just mention that we are able to handle really high power thanks to our reflective designs and our homogeneous cooling. And at the same time, we are able to really reduce the focus shift, which is very important for the industry. Our product line Canon Pulse is another world. It's the world of femtosecond or the world of pulse laser. The idea is to do top-hat or splitting of femtosecond lasers or pulse lasers. And it is fitting well with the industry because it's compatible with the constraint of the industry, meaning the scanners, not all beam shapers are compatible with scanners. We have proved in our case it was working very well. We are preserving the depth of field. This is really important to keep in mind because it's a big challenge in terms of beam shaping. And in our case, it is really unique. We managed to handle the intensity and the phase, meaning that the depth of field you have with your shape beam, you can calculate it using the same formula as your initial Gaussian beam. So it's preserving the depth of field, which is really good for having a robust process. At last, I think it was mentioned just before or two talks before, stabilizing the beam is very challenging, especially for femtosecond lasers. We have created a special feature which is called mode cleaning, and basically it is stabilizing the output beam of any femtosecond laser. Now, Canada hexagon, these are just made to generate the best quality bezel beams. They are simpler components, but still working very well and compatible with any kind of scanners, which is also unique for bezel beams. As a conclusion on that slide, well, I just want to say that in all cases, we have catalog references off the shelf, which you can purchase today. And we are also working at the same time on custom developments on demand on the exact need that anyone would have. At last, what are we looking for? So I want to say, I always start the same way. Well, Cailabs has a kind of DNA of innovation. So we are always looking at new challenges. So if you are an end user and you want to improve your process and you think that kind of new shaping or new features can help, we are really happy to discuss with you to innovate together. At the same time, when you want to have the right product, you have to have the right partners. So we are looking for collaboration with main actors of the field within large projects, meaning European project or national project. We are really happy to collaborate to create innovation together. Now we are also looking for partnerships. We have already some very nice partnerships, but we are always looking for new partnerships. If you want to have your beam shipper one day in the factories, you have to discuss with system integrators. So I am very interested to discuss with system integrators. At the same time, we are looking for improving the performance of the lasers. So who know the best how to improve the lasers and the lasers manufacturers. So I'm also happy to discuss with them. And at last, because it's the standard epic question, what are we looking for? You will notice, Jose, that I try to have always new things in that part. And today I come with two new topics which are of interest for us. They are midterm topics, so not urgent, but still we want to look at that this year. We are looking for ellipsometry tests and equipments. It's very specific. And the other one is mechanical parts providers, but able to do complex with tight tolerances mechanical parts. That's it for me. And now if you have questions, I'm happy to answer.
Thank you very much, Gwenn. Yeah, your wish lists are always very nice because you point out every single step. Now I need this, now I need that. And on the other hand, you are always very well connected now with many EPIC members and also participant of our meetings. So it's a challenge for us to find someone to help you. So at the moment, if you have some questions from the audience, I can already give the floor. Otherwise, it would be maybe time from those you don't know yet, I guess. So for example, Valdemar from ELAS. Valdemar, you want to maybe introduce yourself and say how could you maybe collaborate with Gwenn in the future, close or very far? No, not very far in the future.
Hello, I am Valdemar from ELAS company. Thank you for EPIC for this kind opportunity to participate here in this meeting. And yes, Cailabs is a very useful company for us, I think so. And later or sooner, we will keep in touch. We have first meeting in Photonics West. We had some discussion with Gwenn, as I remember. And we already have some intention to do some tests, but due to this situation of COVID-19, it was stopped and and so on. But I think in later or sooner we will contact.
Yeah,
very
sure.
good. So, so it was not new. Because Gwenn is too much well connected.
Oh no, you know, every time I attend to one of your meetings, I have new connections. It's really nice.
Okay, then we don't feel too bad. Thank you. So, are there other questions from the room? Yeah, and so Natan, please.
So Gwenn, I have a few questions about the presentation. You were talking about depth of field for shaping as an issue, and you said that it is hard to achieve more than the normal Rayleigh length of the beam. Am I correct?
Yeah, exactly. That's what I did say.
Yeah, so at least from what I understand about beam shaping, usually in beam shaping, you're increasing the beam relatively to the Gaussian diffraction limited beam. And generally, at least from our experience, the depth of field increases relatively to the normal Rayleigh length. I mean, if I'm shaping something into something that is larger in terms of spot, it is usually also quite good shaped for a larger range relatively to the tightest spot achievable. Is there something different for your system?
So thank you for the question. Definitely, I was not clear then. What I wanted to say is that when we are doing our beam shaping, meaning that in the processing plane, for example, we will have a 30 micron top hat, for example. What I want to say is that this 30 micron top hat will have a depth of field which you can calculate with the same formula as a 30 micron Gaussian beam. And this is not the case generally with beam shaping because, I mean, it's complicated to manage intensity profile and the phase profile. But of course, the depth of field depends on the beam size. A 30 micron beam will not have the same depth of field as a 100 micron beam.
Sure. And if I may expand, another thing, do you have any data about efficiencies? I mean, there are a lot of internal reflections in the system, I assume.
Yeah. So, it's very, I mean, it's always a choice you have to make. I did present quite a large array of applications and of systems. So the efficiency is very depending on the application. So, for example, for laser beam welding, we are in the measurement precision of the system. For splitting, we have very nice transmission as well. Of course, when we try to do beam stabilization, for example, the beam stabilization is not magical. We stabilize the beam quite well, but it's the drawback is that definitely you lose some energy. So in that case, efficiency would be around 80%, and it's the worst case. So in good cases, it's around 95 to 99% for some systems, and for the systems needing mode cleaning, needing beam stabilization, it will be around 80%.
Okay, thank you very much.
So very good. Are there other questions to Gwenn directly? Yes, from Fraunhofer, please.
Thank you for your presentation and the impressive examples. Would you say that your process or your procedure is mainly applicable to rotational symmetric profiles?
No, definitely not. It's something that I didn't have time to detail, but I would actually even say it's the opposite, because doing a symmetric shape is not always easy, but is much easier than doing non-symmetric shapes. And we are working on non-symmetric shapes. Honestly, for me today, I see that the need is only for high power lasers, like for example, for laser cutting or for additive manufacturing. There is a high interest in non-symmetric shapes, and we are working on that. Actually, just behind me, I have the poster of a European project we are involved in which we are looking at non-symmetric shapes for mainly for high power applications. We never had any demand for femtosecond lasers, but we could do it as well.
Thank you very much. Very interesting.
Very good. So further connections maybe in the close future. Now it's maybe time to introduce Oplatech. So Kimmo has some issue with the camera, but we know that he's listening, sounding clear. So maybe Kimmo, you can introduce yourself.
Okay, can you hear me?
Yes.
Great. So my name is Kimmo Solehmainen and I come from Finland, which was the happiest country in the world before the pandemic, but I guess we are still, because now we can isolate us, to our summer cabins beside a lake, like I am at the moment. Okay, well, my company Oplatech offers contract manufacturing services for photonics. And we have manufacturing capabilities for fiber drawing, glass molding, thin film coating, and precision mechanics. Our glass molding service is quite competitive for producing beam shaping lenses, especially for medium and low sized production volumes. And then we can also provide the lens holder mechanics through our CNC workshop. So we can provide the related assembly services as well. For example, attaching these beam shaping lenses to lens holders to deliver lens assemblies. So basically, this is it. And our CNC precision mechanics workshop might be of value to Cailabs.
Maybe yes, you know, it was the very new wish list point. What do you think, Gwenn?
Yeah, sure. I'll be happy to discuss that as well.
Very good, very good. So Kim, it was the right time to
Yes.
to mention, to go out of your summer box or whatever. Maybe we don't want to see it. Okay, so thanks a lot, and then we maybe go forward with our agenda so that we don't stay too much on the back side. So now it's time for Roy McBride from PowerPhotonic. So Roy, are you ready to roll?
Sure, yeah.
There you are. So the floor is yours.
Okay. How do I don't see the thing to share. Can you flash
Just
it?
the bottom, you go down, there's the green
Oh,
button.
gotcha. Yeah, I've got it. Screen 2. Can you see that?
Yes, there you go.
See if I can pull you guys up again. Okay. So I'm going to talk to you about high performance beam shaping for laser applications. Now, most of the applications that people usually think of when you think of laser beam shaping are in industrial applications like laser cutting, laser welding, arcing and drilling, laser liftoff, and additive manufacture. But there are also quite a wide range of applications for laser beam shaping in other areas, such as in imaging and laser projection display, generate where you want to homogenize the beam to get a very uniform image. In advanced microscopy, where you want things like light sheets or arrays of spots for novel forms of imaging. In defense, where you want beams to either illuminate or sometimes destroy the target. In science, for high energy pump sources, optical tweezers, applications like that, and also medical applications, such as skin treatment and tattoo removal, where it's important to have a very uniform beam to avoid damage to the skin. And the requirements for beams in these applications are fairly consistent. Usually customers want high efficiency, which means low scatter, low absorption loss. They want high fluence and high power handling. These days, a lot of applications have moved to multi-kilowatt, beyond 10 kilowatt. And also we get multi-joule applications these days too. People want a free choice of input beam. Customers don't always have a nice single mode Gaussian beam. So you need beam shaping techniques that can be tailored to the source beam shape and profile, and also the source spatial coherence. Some sources present real challenges in terms of spatial coherence. And also you want to tailor that output beam. That's the fundamental requirement of beam shaping. So customers want precise control of beam shape, output beam shape and profile. And we approach this using free-form silica micro-optics, which we design and manufacture on our site in the UK. We manufacture these using a direct write, laser direct write process that we developed ourselves and developed equipment to implement it, which all runs 24/7 lights out in our factory. Now, this free-form laser direct write process gives us a very wide choice in the range of surface profiles we make. Essentially, we're doing CNC machining of silica glass. So we can produce pretty much any surface profile that we need to implement our designs. And that gives us a great deal of design freedom in the kind of beam shapers that we can make. It frees us from symmetry constraints, and it allows us to realize a very wide range of designs, providing a wide range of functionality. Also, being a direct write process, there's no hard tooling, there's no design specific masks or molds, and this means that we can trial and iterate design. So usually customers don't know the precise beam shape they need, and they want to do trials and optimize that design. So this manufacturing process lets us do trials, iterate and optimize the design. And then once the prototypes are validated, we can go through to volume with the same fabrication process. No requalification required. And some byproducts of the nature of this fabrication process are that it gives very precise fabrication, very low scatter and low loss. It gives high performance optics. The laser fabrication process reflows the surface at the end of the process. So you get a very high quality of silica surface, which means it handles very high fluence and also very high CW power. So our optics typically routinely handle more than 10 kilowatt CW, more than 1 joule nanosecond, picosecond, femtosecond, even not just in IR, but in green as well. And being silica, they handle a very broad range of wavelengths. So the classic configuration for laser beam shaping is you place a beam shaper before a Fourier lens, and you design that beam shaper starting off with considerations of the source spatial coherence, as well as the input and output beam profiles. And in terms of the options based on source spatial coherence, there are completely different classes of beam shaper. For single mode beams, where you want field mappers that stretch and shape the beam into its final shape. And for multi-mode beams, where essentially you slice that beam up into small patches, shape those patches, and overlay them. And in both cases, you care about not only the shape of the output, that is whether you want a rectangle, a square, or a line, or a circle, but you also care about the distribution in that output as well, which is whether you want a flat top or a Gaussian or something more complex like an M profile or a trident, or as we've seen earlier, a bezel beam with a very long propagation distance. And PowerPhotonic, we can design and manufacture beam shapers for different input conditions, single mode or multi-mode, for different input beam profiles, and we can tailor all of these for the different kinds of output beam shapes and distributions that you want. So I'll just go through a couple of these. Also, obviously, there's a very wide range of beam shapers that can be generated in this way. So I'll just go through a couple of examples. First one being an application for high power fiber laser welding, where a rectangular spot was needed in a very high power system. And one of the challenges with high power fiber laser beam shaping, the source beam is neither purely single mode nor properly multi-mode. Typically you see, between 5 and 10 modes in the source. So using pure field mappers doesn't necessarily give you the perfect beam profile because the source can change. But if you use a typical homogenizer, you can get diffraction artifacts. So in this case, we designed a concave toroidal lens array to give the right results in terms of source spatial coherence, in terms of having no patterning on the output. We give the right far field beam shape at the process plane, and also to avoid any retrofoci, because this had to go into an industrial process head at 10 kilowatt, and we couldn't afford any hotspots in return. And this gave the beam shape desired, which improves weld quality in very high power systems. And then another example here showing the extremes of fluence that these beam shapers. This is a homogenizer to go in the pump beam of Rutherford Appleton's Gemini laser, where the beam it had to homogenize the beam into a circular flat top and handle a 532 nanometer 25 joule femtosecond pulse, so a very extreme regime. And being a pump beam, efficiency was very important. So this beam shaper gives over 98% efficiency in the system. The type of beam shaper we use here has no zeroth order, so you get a very uniform beam with no spike in it. And it's very reliable in these high fluence environments, so it gives a very long lifetime for the system. So that's a quick summary of the kind of beam shapers that PowerPhotonic can do. So key points being, we can make application-specific beam shapers that are tailored both to the source properties and to the process requirements at the output. We operate with a very broad range of lasers, CW to femtosecond, UV to near IR, and can handle the extremes of power and fluence. And what we're interested in, well, we're interested in people with problems to solve, people that need solutions, people that might want to partner with us. Basically anything, any new challenges in the field of laser beam shaping. Thank you.
Thank you very much once again for a great presentation, and we are gonna have quite a lot of debate now, but the most important thing here is, what kind of challenges do you have for the system integrators today in the room? Because we want to identify what they need. What would be the right question you would like to ask companies like, for example, Hyers, who makes femtosecond lasers for tattoo removal, for example?
Okay, yeah, well, we'd like to know what the performance challenges you have in your systems, basically, because we normally operate with systems integrators who come to us with they come to us with a functional requirement, and we design a beam shaper for them. So yeah, we'd like to know what functional challenges they have in their system.
Let's do that. Let's do that. This is fun. William, thank you very much for joining the meeting this afternoon. We would like to know from Hyers, first of all, what you do, and most important, what challenges do you have in the field of beam shaping?
Hi everybody. Thank you, Jose, for the introduction and for this and all the EPIC team for this meeting. Thank you. I missed your name, Roy. Sorry. Thank you, Roy, for the kind presentation. So I'm working for Elysium in France, and we are doing systems for tattoo removal and other aesthetic applications using lasers. And today, so we are interested in, I would say, ways to have homogeneous beams on the skin. So that's interesting. And so we are developing lasers at 1064 and 532 nanometers. And today we are just using standard multi-mode fibers, so 100 micron core diameters. And in order to have a better understanding on the process and interaction between the beam and the skin, we are looking for new stuff to first study the impact of the beam shape on the process and on the tattoo removal, for example. And so using optics to homogenize the beam is very interesting for us. So the first question I could have is, do you have such optics that can be used at 532 nanometers and 164 nanometers with the same components? So that's the first question.
Yes, we do. Actually, the beam shapers we use for that kind of beam shaping, in fact, the type that we used in this application here, we call prime. And it's a hybrid between refractive and diffractive optic. But one neat feature about it is it's essentially achromatic. So you have something that behaves like a DOE, but it's essentially achromatic, so it can work simultaneously at 1 micron and 532. And we use these, we currently sell these into tattoo removal, and they work well with short pulse beams in green and other wavelengths. Yeah, so I think we should definitely talk. That sounds like a very interesting application that you have.
Yeah, and you have to see what they can do. It's actually quite a fascinating company, Arizona. Roy, I have a question from the chairman and CEO of Jasper Display, my very good friend Ken Tai. Hey Ken, thank you for joining us today. He's saying, are you considering a digital approach leveraging silicon substrates, electronics, and software?
For us, we don't, because we leave the system integration to our customers. So we focus on the design and fabrication of our optical elements, and we let our customers do all of the assembly design and integration. So far, we've not tackled those challenges.
Maybe some nice partnership on that, because Adrien is joining us today from a company that I really love, Lighttech. Not only software, but also they make quite fascinating instrumentation. Adrien, thank you very much for joining us. What kind of partnerships do you foresee you can make, and what can you do with Roy? I think we have some sound problems all the way from Lighttech. I promise I'll get back to you. But during the discussion, I was chatting offline with my very good friend Axel from Qioptic. Axel, thank you very much for joining today. What do you think about the meeting so far, and what kind of connections can we make, especially in the femtosecond laser regime for ophthalmology?
Hi, Jose. Thank you for the introduction. So I was more in this meeting for curiosity and what's possible to do with beam shaping. So we are currently in ophthalmology mostly focusing on having a diffraction limited focus as small as possible. And I still have to think about what can be done here. So there's no particular question from that side.
What in the field of, well, very many people know Qioptic now. In the field of beam shaping, what kind of partnerships, what kind of challenges, what kind of cooperations, what kind of room for cooperation do you have?
So I think that's more up to my colleagues from the who deal with the laser application directly with the laser material processing applications, so for the industrial optics. So I'm a specialist on the biomedical stuff.
Axel, on the 29th of June, I'm organizing an online technology meeting on lasers for ophthalmology, and I want you to be one of our speakers then. And Roy, we're going to move to the next presentation. With Roy, we're going to move now to asphericon, and afterwards, we're going to have a bit of a debate. I want to understand from the companies making axicons and from the companies needing axicons, what being shaping the need for each application. Sabrina, thank you very much for joining us today. The floor and the attention of everyone goes to the capital of optics in Europe, goes to Jena. And you need to unmute yourself. Yes, we can hear you.
All right, good. Then let me share.
You want education or being shaping, check the YouTube videos of Sabrina, quite spectacular. Yes.
All right, can you see the screen?
Crystal clear.
Everybody? Jose, can you all see the screen?
Yes, we can. Crystal clear.
All right. All right. Then, yeah, thank you again for the introduction. Yes, and please all go check the YouTube videos. It would be my pleasure if you click a thumbs up. That would help. But let's come back to today's topic, and it's all about beam shaping, and we have seen a lot of different beam shaping options. So I would like to introduce to you a refractive version of beam shaping, because this is what we do. For all of us who don't know asphericon, we are not like only in the field of beam shaping. As our name says, we mainly manufacture aspheres. This is our core competence, but we can do any kind of optical components, and we can be in the supply chain all the way from the design of the component, coding the housing, manufacturing the metal parts, also designing the metal parts, and doing the assembly in-house. But if we have a look at the beam shaping options that we offer, all of our beam shaping components are following a refractive approach. So we don't have any energy losses in our elements, and we can use them for a very broad band of wavelengths. And as you can see, we have different beam shaping options, but for today, I would like to stick with you on the airy shape, which converts Gaussian input beams into top hat in the area of the micrometer level. The airy shape itself is based on a faceplate, or the basic idea comes from the faceplate microscopy. And what the airy shape does, which is the very dark element that you can see here in the picture, is it will convert your incoming Gaussian beam into a Bessel sink function. And then we use a simple lens, and this lens will do a Fourier transformation, and so you will automatically achieve a top hat in the focal spot of that lens. So this is what your beam profile or the intensity distribution would look like if you just have your single lens do the focus and you're using a Gaussian beam. Light comes from the left and it goes off to the right. And if you now implement the tiny airy shape, you can see such a crazy intensity distribution. And if we now normalize this, you can see that there are several areas of interest that can be used in all those fields that we have already touched today in the laser material processing or in medical applications and so on. You probably know better than I. And you can see that we can achieve several top hats plus an area where you have a donut, and you still have a beam waist by just implementing this one element. This is another picture that shows that all these profiles really appear, because what you've seen so far have just been simulation pictures. But the gray pictures here are microscopic pictures of single ablation shots. So you can see that they are in very good agreement with our simulations, and you see the donut and different top hat spots plus the beam waist. Our airy shape follows also a very modular approach, which means you can use it with all the other elements from asphericon. You can use it with our beam expanders or with our fiber collimators, or you can also use it with a free beam, and you can use it with other elements available in the system, and you have the ability, due to our cross-system adapters, to directly connect it with other elements in your setup. So it can easily be integrated in any existing setups without any changes you have to go through. And the size of your top hat, the diameter, is then determined by the focal length of your lens. So if you wish a very narrow and very small diameter, you just choose a short focal length of your lens. Or if you wish to have a wider spot, a bigger diameter in your top hat, you just go for a longer focal length lens. As we know, in some applications, working distance is tricky and is important, and you have less space. You can do a little trick. You just implement, after your airy shape, you implement another beam expander in reverse to decrease the beam, and this will help you to choose for a shorter focal length lens, and you will still get the same diameter in your top hat. So just a little help. This is the airy shape as we have it in the market and as you can buy it so far. It converts your Gaussian input beam in that Bessel sink, and then you use your lens, and you will have these different beam profiles, the donut, the top hat, and the beam waist. But a lot of customers ask us for a squared refractive version. So we, of course, were working on this, and we found a solution how we can also have a squared version of an airy shape. And as you can see, the simulations are very promising. So we built one and tested it, and also the measured beam profile is in very good agreement to our simulation. So this should be one of the next products that we would like to introduce to you, but this is the favorite one for Jose. He always wants us to tell you what we can do for you, and I hope I could show you what we can do for you. But on the other hand, what you can do for us is, I would like to know what beam shaping is really needed. What shapes do you need? What do you expect? And what do you need for your application to make it really better? And as you can see down here in the pictures, the blue ones are again simulations, and the ones in the black boxes show real measurements. So I think there is a lot of opportunities and there are a lot of options. So just challenge us, let us know what beam shaping means to you and what you really want from your beam shaping element. So thank you.
Thanks a lot, Sabrina, for your contribution. So as usual, there is a bit beam shaping, refractive, so transmissive or non-transmissive elements. We have here a few participants to the party, so that's of course the topic here today. So is there someone who wants already to comment on, of course, the wish list of Sabrina, because she wants to know which beam shapes you need. So we heard a bit already from the tattoo removal industry, but if there's someone else who wants to comment on this or what Sabrina said, because if it's not the case, maybe it's time for Adrian, that now should have the microphone working.
No wishes.
So from LightTech.
Yes.
Yes, there you are. So maybe you can introduce yourself before you lose the microphone again.
Sure. So my name is Adrian. So I work for a company called LightTech, which is actually the European supplier for Synopsys optical engineering software. So we have software for optical imaging, radiometric analyzing and illumination. You have software for photonics, and we have software for car industry. We also have, we provide some measurement analysis of the BSDF, for example. We also sell some instruments, so we do measurements and we sell measurement instruments. And so for this topic, so one of the software by Synopsys is called Code5. So for people who are willing to do optical design, so for example with lasers, then we can provide you with a very nice software which allow you to have very powerful algorithm for optimization and tolerancing, especially if you combine the algorithm for optimization with the fast wavefront differential tolerancing algorithm that we have. So this will allow you to design your optical system being less sensitive to manufacturing and assembly error, so without the need to iterate between optimization, tolerancing. So this is for the optical designers. And we also have a very powerful tool which has been developed at the base for the NASA, but which is called the beam synthesis propagation, and which is a very nice feature which will allow you to do physical optic propagation. So it's based on the beamlet decomposition of the complex field, and this will allow you to model the propagation and the clipping of your laser lights even within non-sequential surface range. So if you have this kind of problems like clipping apertures and so on that does not compute very well with other algorithms, then we are confident that we have with our tool included in Code5, so beam synthesis propagation, you can deal with this kind of problem. So we are confident in this kind of stress. So if you want to try it, and so just give it a try, please contact us at LightTech, and you will be able to model.
It is a great partnership that we can do there. For me, the time has come. I learned a lot, and we're going to have one more presentation on HoloOr, but the time has come. The time has come to have a nice discussion. And I'm going to ask my two friends from CSCM and ILT, which I am very happy that they are here. I ask as a personal favor, I'm very happy that they are here to lead this discussion. I want to understand what beam shape is needed for each application. It is clear right now that we have laser beam welding with donut shape, engraving with beam splitting, glass cutting with bezel beams, and surface texturing from line top hat. But I want to have this discussion. David, why did you join this meeting today? What kind of cooperation shall we start after this?
Yes, thank you. Thank you for being part of this discussion.
You hear me? Yes.
Yes.
CSCM is an R&D company, so we are very active in very different applications. I have different clients. So in our case, it's not that we sell something which is concrete or a product. So I'm here to learn about what other partners or are doing, what they can provide. And I'm especially looking for manufacturers. So we do a lot of design, specific design. We have our own tools, but we are lacking means of fabrication, of high quality manufacturing, of freeform optics, diffractive optics, refractive optics, and also the applications. We are more here in the proof of concept cases or prototypes. So we're looking for partners who can quickly react and provide us samples so that we can show the proof of concept, and then that leads to another industrial case.
Sabrina can help you with this because that's what she does. But can you give a challenge? Because right now we have HoloOr, we have PowerPhotonic, they're all taking notes. They're like, I have to give them a challenge, something difficult. So I call it the Santa Claus Christmas list.
The challenge in diffractive optics, it's precise control of depth. That means high efficiency. We can do a lot of theories and computer-generated holograms, but efficiency is here the key point. So precise control of depth and multi-step optics. For freeform optics, I saw that many manufacturers are limited what concerns asymmetry or steep angles or something like that, something which is not perfectly symmetric. And for other things like refractive optics, I'm thinking for like microprism arrays, micromirror arrays. The structures are rather simple. It's a plane, tilted plane, but I need high surface, low roughness, so high quality on the surface and precise angle.
That's a lot of challenges in one, but I take it that the big one is the precision, right, Sabrina? How can you help companies that demand very high level of precision?
I would say that we are on a very high level of precision, and the ones that would be or that we would love to check for you and would see if we can handle the challenge would be the freeforms. So if you have something really in mind that we could check, because it's very hard to give you an estimation out of the pocket right now, we need to see what you really want to achieve in terms of asymmetry and so on, and then we could address this to the technology group, and I could give you feedback if this is something that we can handle and we can do. And another question from my side would then be, what means quick to you? I mean, prototypes, of course we do prototypes, we are used to that, and especially in freeforms, it's always prototypes, but what means quick? I mean, freeforms are challenging.
No, thank you for your readiness. No, quick doesn't mean that we need it the next day. It's just the readiness that you're not just selling out of the box, but maybe we have a special design need and you would be willing to discuss that, let's say.
In terms of freeforms, we do all customize. There's nothing that we have as a out of the box and we only do the one thing. It's all what the customer needs, and the customers challenge us and we try to further develop the technology. The technology is there, but sometimes you can push it to the border and get
Sabrina,
more out of it. So
challenges. So I'm gonna give you more challenges. I'm gonna go to my friend
Yes, please.
Aachen. I'm gonna go to Fraunhofer ILT. I know Fraunhofer ILT is my key member when it comes to advanced laser manufacturing R&D. You have been very active on laser beam shaping for different industrial processes. If you could identify what is the Santa Claus Christmas list for Fraunhofer ILT and your partners.
Well, if I can write a list. My biggest point would be the armchair distribution, because we are doing a lot of calculation for the inverse intensity temperature profile calculation. So if you want to have a homogeneous temperature profile, you need an armchair-like intensity distribution. And this intensity distribution changes with the scanning speed. And if you're making a turn with your scanner, with your galvanometer scanner, then this shape will change. So you would need a dynamic type of armchair in terms of size and resizable, a resizable couch or armchair, dependent on the area. That would be my biggest wish from Center.
That's a good one. I think I have Dirk smiling, so maybe he can help you. I have Roy from PowerPhotonic taking notes. I think we're going to make a lot of introductions there. I'm going to go now to Hanover, the other one that we have very active in the R&D for laser beam shaping. Lars, so far we have heard a lot of different technologies. We have one of the best ones, HoloOr, still to follow. We have heard a lot of different technologies for beam shaping. If you could identify what is, for the partners of Laser Centrum Hanover, what would be the Santa Claus Christmas list, the biggest challenge you have for these people?
Well, you will probably get different answers from different people, because we're set up from the machining down to optical design, optical systems, and even the coatings. From my point of view, I would have a question to all these more and more monolithic and integrated optics and complex freeforms is how about the coating processes for these complex freeform optics? You need a high precision on your spectral characteristics, and if you have all these complex surfaces now, how do you reach the precision that you need on these surfaces for the coating? Is that a challenge for you, or is that something that you see you can still do with the current technologies?
Many people could answer that question, but I'm going to ask first asphericon and then SUS micro-optics. Asphericon for the very complex freeform optics they can make, and then SUS because they can make the wafer level freeform optics. Sabrina, how do you deal with this, with the coatings on complex surfaces?
I have to be honest, I have to address this question to the team. I'm sorry, Lars, I don't know. Because I'm so far away from the freeforms in our company that I don't really know what's going on with the coatings, if there are any challenges, if this is easy to handle, if they have solved all the problems, if they are often facing some. I really don't know. I only can address this question.
We had a whole meeting on freeform optics a couple of weeks ago, an online technology meeting. It was, Lars, the biggest challenge that we have had so far, the addressing, especially when it comes to freeform wafer level micro optics. And for that, I'm going to ask my friends from Neuchâtel. They have made a center of excellence for manufacturing of freeform wafer level micro optics. Wilfred, thank you very much for joining. Lars is wondering, how do you deal with coatings when you have some very complex surfaces?
So for now, that's a very good question. So sometimes we have very steep surfaces. So for our collimation lenses, for example, with very steep surfaces, and we had to work with the suppliers on processes where it sticks to the side. Well, so that was not easy. Yes, so this is a good point. So freeform optics, so this is more for replication. So we make replicated freeform optics mostly for automotive applications, not yet for beam shaping. For beam shaping, we are working more with classical etching for high power applications and diffractive optics, of course. So we make for excimer lasers diffractive optics since 20 years. So this is a very good business for us. And so in these air coatings is always a good point, yes. So LZH is very good at that too, that we noticed that. So
yeah, and it's a great company visit that I recommend everyone to do, even myself. As soon as the virus is over, I'm going to Hanover to visit you guys. I'm going to go to Vilnius because I want to ask the same thing to Valdemar. Valdemar, CTO of ELAS, how if you could write the Santa Claus Christmas list right now for the workstations in micro machining that ELAS provides, what would be the one that you write for beam shaping? What would you ask? What would you challenge these people with?
Okay, so let's say this will be not directly related to things that we are doing, but one challenge that I met from scientific applications to shape the beam to have free beam shaping. Let's say when we have some triangle and to put the beams directly on the corners on the triangle. Because I saw that it's possible to shape the beam to have a square shape, but let's say to split the beam, let's say to have beams on the square, to have on a hexagon, but how to make a beam shaping to have on the edges on the triangle without the central point inside. This is the main challenge from my side.
It is a big one. I don't know if anybody wants to comment on this. Because I did, yes, I have my friend from Hamamatsu. Thank you very much, Thomas, for joining today. I think you have to unmute yourself so we can hear you.
Yes. Okay. Thank you for introduction. Yeah, I mean, we talked about now a lot of static beam shapers. So Hamamatsu, for example, has a spatial light modulator, ACOS-based spatial light modulator, and it's basically a dynamic, addressable, refractive, diffractive element. So you can basically beam shape whatever shapes you would like to have. Of course, efficiency and so on is always needs to be taken into account. But for example, this triangle might work, and armchair we heard distribution. I'm not sure, of course, I'm not really fully in the application, but I could imagine that that would work too. So well, we provide the technology, basically, the modulator, but with some partners, you surely can like calculate the right beam profiles and phase patterns you need for that. So that could be a solution.
Roy, many challenges today on the table. What do you have to say?
Yeah, I think PowerPhotonic could provide a beam shaper that splits the beam into 3 spots in a triangle. Yeah, I think that's quite possible. I can see the challenges, but I think our technology can do that.
Roy loves challenges.
Yeah,
I think definitely there is
why
an
we're here.
introduction there to be made. And we go to the last, I'm having so much fun. I feel sorry for saying this. We go to the last presentation of this amazing meeting. We go back to Israel. We go to Nate. Thank you very much for being with us. I've seen the donut and seen the line and seen the flat top next to you. It's been so inspiring. The floor and the attention of everyone is yours.
Thank you very much for this kind introduction, Jose, and for everyone for lasting to the end. So I'll try to be brief and concise, but I do have some points that I would like to discuss about beam shaping. So for those of you that do not know us, do you see my screen, by the way? Sorry, Jose? Okay, great, because you're mute. Okay, so for those who do not know us, I'm Natan from HoloOr, where the words, I think,
let us go to presentation mode so we can see you.
I'm trying. 1 second. Oh, better now. Okay, but from the start.
Yes.
Okay, so we are a diffractive optics manufacturer. HoloOr was founded in 1999, making us now, this is our 31st year, more than 30 years of excellence. We are the first commercial manufacturer of diffractive optics for high power. We started with the mid-IR at 10.6 when lasers were still weak and relatively expensive. And as the laser market grew, we grew up with it through a variety of applications, from the aesthetic field and the material processing field to sensing, R&D, more or less every application. We have many customers that are mostly laser integrators in a diverse distribution all over the world, including the East, Europe, the US, and more or less everywhere there are laser integrators. Basically, we have seen quite nice steady growth in the last few years, and have added many new capabilities, including the ability to make micro-refractive optics, at least for the diffusion and the homogenization. And we also have the capabilities to build sub-modules and sub-assemblies, especially for glass cutting and increased depth of focus. So basically what HoloOr does is we both design, develop, and manufacture diffractive optics and micro-optics for the shaping of high-power laser beams. Basically, for those of you that are less familiar with them, diffractive optics are thin optics that utilize the phase manipulation of the wavefront to create any desired intensity distribution at the far field or the focus of focal length. I believe most of you are quite aware of them. The main advantages are the fact that the angles are completely accurate. There is no tolerance on angles for our elements, which means that no matter what, if it heats up, if we have some manufacturing tolerances, the angles, the EFLs, the splitting angles for splitters or the diffusion angles for diffusers are constant. They're rock solid. Their accuracy is determined by the lithographic manufacturing, which is more than 10⁻⁵ of the range. Other advantages of diffractive optics that are easily manufactured in batches, with all batches sharing the same characteristics. Therefore, they are very reliable for larger system integrations when you have multiple tens or hundreds of machines that you need to produce. They're basically click and play. Once you characterize the initial characteristics of the shaping optic you require, we can easily design it, and it will be stable within a spec range that we guarantee based on our simulations. One of the main advantages of us as a manufacturer of precise optics for shaping is that our simulations are intimately tied to our production. We have very good connection between the simulation side and the production tolerances. Therefore, we can guarantee a spec that will be for sure withstood, regardless of the end test, which we do, of course, for every element. We cover all optics from the deep UV 193 nanometers up to 10.6 microns, using both fused silica and zinc selenide optics as required. We can also do some things in higher IR grade fused silica like Corning 7979, which are useful for 2.94 for aesthetics. And our solutions as diffractives are very flexible because we can stack multiple shaping optics and multiple shaping functions on one surface. Thus, our capabilities are to mix and match all shaping solutions. For example, splitting with shaping, or even focal shaping with splitting is possible. Now, our selection of products is very wide. I will not go into our selection of shaping solutions, but generally we have beam splitting to any number of arbitrary spots, including higher efficiency beam splitters utilizing multi-level designs, which are highly useful for welding, for example, the dual spot welding of our heads family. We have beam shaping both for coherent single mode beams, like mentioned by Roy, using our diffractive beam shapers, which are absolutely accurate. And they can provide arbitrary shapes, including triangles, squares, circles, U shapes, C shapes. Actually, we have quite an interesting experiments with C shapes regarding welding and its usability. We have diffuser shapers for higher M-square beams, including things like this blazing diffuser shaper, which is highly useful for brazing processes in the automotive industry. And of course, we have our diffractive axicons and our diffractive vortex lenses, useful for the generation of Bessel beams without any apex. All elements are flat, have very high laser damage threshold that is almost the same as unpatterned fused silica. And elements are also compact and lightweight, and usually most shaping functions can be achieved by one element and one field lens. For some more complex requirements that the industry required, I remember, Jose, last time, a year and a half, we had a workshop where you asked me, when will HoloOr offer a Z top hat for glass cutting? So half a year afterwards, we have launched our Deep Cleave series, which offers a very nice Z top hat distribution. This is, let's say, industry calibrated. It's not a centimeters range. It is more typical from 1.5 millimeter to 2 millimeters. We can, of course, do more, but this is usually what people try to cut in glass, and focuses down to 2 microns of spot size over this range. It's a very simple, nice module, and can replace your high power objective for the purpose of glass cutting. So basically, we at HoloOr are interested. I'm sorry, I didn't make a slide for that, but we're interested, of course, in what laser integrators need as a solution. And for example, I was very interested about what Iris wanted for the aesthetics. We have exactly this solution, the broadband diffuser, which can diffuse for both for 532, for 1064, and for any wavelength at the same angles. Triangular shaping is something we have done in the past, including triangular splitting. Mostly the issue there is lower efficiencies, but for those that require this, it is a routine process for us to do this. It is not a special sort of customization. It is within our normal, let's call it NRE process, which is generally low cost and very quick prototyping. So thank you for this opportunity, and I would love to hear questions from anyone.
Thank you very much, Natan, for your talk, and also for already interacting lively at the beginning of the so during all the duration of the meeting. So I would like to say that Valdemar, I guess he will be bombed by requests because this triangular shaping is not that of a challenge, or at least is something that our manufacturers here are already into it. So be prepared to some connections. Are you surprised, Waldemar, or is something that is positively surprised at least?
Yes, I am not very surprised because, yes, of course, it's possible. But as Natan mentioned, that diffraction efficiency is not so high. So how about to get the diffraction efficiency about 90% of 95%? So that's why.
With
that's
single
where
mode?
is the
Sorry, with single mode?
Yes.
And without ruining the M square, correct?
Yes.
And not sure it's physically possible. Yeah, but that's an interesting topic
Yes,
for
but
discussion.
the maximum as possible.
Okay, I'll get back to you.
Okay, maybe Roy wants to comment on this as well, or
Yeah, well, for single mode beam shaping, then you want to use a field mapper, really, and that can give you, 99% efficiency plus, but it's a different kind of solution. Yeah, we could offer that. And yeah, we've got quite a wide range of options in that category. So you get in touch if you want to follow up.
See, there is. I told you, Valdemar, there will be some people talking afterwards.
The single mode, circles, discs, flat tops, donuts, lines, squares, rectangles are all possible with high efficiency.
Good. Is there anyone else who wants to comment on Nathan's talk? Because I know that Hannah from Aarhus University, she didn't speak yet, and she's here. She listened to all the presentations. Can you briefly introduce yourself and also JPIX maybe, and then see tell us what is interesting for you that you hear in this meeting?
Yes, thanks for giving me a short moment to talk. I'm from Aarhus University, but I'm speaking for JPIX today. We're basically a consortium of people putting together the photonics integration technology in Europe, focusing on the indium phosphide and silicon nitride part. I'm mostly here to see if there is any opportunity in this community for integration or to take some modules, or I'm thinking maybe monitoring or analysis to an integrated optics, integrated photonics application. So I'm interested if there's any application, any opportunity out there that might be addressable by integrated photonics, which could be the filtering on chip, phased arrays, on chip analysis, maybe on the side. I know we're lacking a little bit in the high power aspect, as the most of you are addressing, but there could be some opportunity there. So you might want to check out JPIX and the technologies that we offer, and also the partners that we have in simulation software and manufacturing and packaging and design.
Very good. Thank you, Hannah, for the introduction. So something that you reminded to me, actually, so staying on the high power application, we heard today many times that talking about laser beam welding, and there will be a really dedicated event on 19th of June, another online meeting. So please keep in mind, we don't want to only talk about the traditional laser beam welding. We wanted to go a bit beyond the frontiers, but we didn't want to scare the traditional users. So we didn't say beyond the frontiers, but that's what we want to hear. So all the people here that talked very often about it. So we were at least Roy and also other speakers that talked about it. So of course, Gwenn, and please keep in mind this, there's the other meeting, and then also medical laser next week for medical application. We will have also William speaking there. So it's a bit a reminder. Then I wanted to ask maybe Antanas, what did you hear? So you were at the very beginning. So were you a bit impressed about other beam shaping, or do you think you can also compete with all these people who wants to talk with Valdemar afterwards? Without speaking Lithuanian, because the others are...
Okay, to Valdemaras, I should admit that we cannot build triangle. Pity, my bad. But to others, I think that we in our side we do very similar things like HoloOr does in a little bit different way, and their flat top, especially rectangle, is much better than ours. But in any way, I think that both approaches have very good future, because it is really suited for high power lasers, high power technologies. And we are getting requests for quite crazy conditions of fabrications. So that's why, like I showed on previous meeting, we build also very crazy distributions, like smiling faces and so on. And I saw one smiling face today as well. So I think, in my opinion, the diffractive optics or geometric phase optics has a really good future in laser technologies.
Very good. Then I see Florian appear, maybe from Coherent Munich. Maybe he can speak now. Florian, can you try to unmute yourself? That we tried earlier and it didn't work. Maybe I unmute you, but I'm not sure if it's going to work. No, so maybe let us know if you are better in the connection, because now I have a bit of a question for Natan still. Then I give the word to Jose. We always, so you are there on the market already since a long time with HoloOr. And there is always maybe sometimes at the beginning the issue of lead time because of especially customized products. How do you see the situation now by HoloOr? Did you in the past years, let's say, optimize this process, or do you think there is still room of improvement, or what do you think was the path so far?
You're talking about the litho process specifically?
Sorry?
I'm sorry, the production process, the litho?
Yes. So the lead time from ordering till shipment.
Yeah, so I believe when I came here to HoloOr, it was 4 years ago, the lead time was around 10 weeks for most items, and I believe we're now down to 6. And when for uncoated optics, we went down to 2, the most of the lead time is coating time. So the next stage,
so it's not your fault.
It's actually not. No, it's our fault. Yeah, but actually, it's the major issue. So if there was some fast coating service that at reasonable costs, usually that's the main issue. For high power optics, it would have been very interesting. We're always looking for partners, especially in the Eastern Baltics, because there is a nice industry there. But really, the only way to reduce lead times significantly for us would be to go to in-house coating, which we're maybe considering at some point, but not right now.
I see. Then we have the solution then. This I didn't know. So now everybody heard about it, also in the Balkan side, and so in the Middle East side. And so now I guess the message is sent. So Jose will send the final message.
Thank you very much, Francesca. Wow, what a chair. Wow, thank you. She's fantastic. We are so lucky to have Francesca on Epic. One thing, I learned a lot today, but you also realize how many connections we had to make. So much work. After a meeting like this, there is so much work now making all the connections, but please make sure that you follow up. I'm going to introduce many of you to different companies. All I ask you as a personal favor, make sure that you exchange opportunities, you have a conference call, and you try to find reasons of working together. That's what we want to achieve here. Myself, I think there has been a lot of learning points together, potential room for collaboration. At the same time, I was chatting with you on WhatsApp, checking the YouTube channel, talking to many of you in the Zoom channel as well, in the chat. I took notes as well. And these are the notes that I took today. Basically, for me, one of the learning points I wanted to achieve was to talk to the different system integrators we had in the room about what were the needs on the laser beam welding, on the donut, on the engraving, on the beam splitting, on the glass cutting, on the basal beam, and the surface structuring for the line top hat. What the discussion has been on one hand has been on the power, and especially in the stability for the high fluence. On that, I took a picture on PowerPhotonic. I was quite impressed. I'm always very impressed with what they can do. On the second is the robustness. That was very clear from the system integrators. That was very clear from the beginning beginning from ILT, from PLX. I think there is a need there, and I think both PLX and Optogama did present fantastic opportunities there for collaboration. There was a key challenge there, which is on the armchair from Fraunhofer ILT, and many of you really think that they can provide a proper solution, so I think that's obviously one of the key challenges. On the pulse, especially when it comes to surface structuring, having the right top hat, having a very accurate top hat was obviously clear. For many of these solutions, especially surface structuring, we need to go to beam splitting, we need to do multi-beam solutions. Having an homogeneous multi-beam solution has also been dramatically seen by many of you as a key challenge, especially from the ELAS company. Also accuracy, metrology, accuracy for especially very complex optics. And Sabrina from Asphericon was very happy with that challenge because it's one of the unique selling points. Coatings, from the beginning we started talking about coatings, especially IBS was talking, Optoman was talking about IBS coating as a key unique selling point, but the coating free-form optics, how do we address this? And the high temperature challenging. On the pulse shaping, I was very impressed with the company from MWTechnologies. I think many of you actually were impressed with this. I got the comments afterwards, especially with the use of switching, turning the pulse shape, the pulse time for managing different colors and surface structuring. There's a challenge there, which is specialty fiber, which MWTechnologies addresses, and many of you address as well. We're going to have a meeting on that topic. But so many potential collaborations, so many learning points, such a good meeting. And the best part, not only the best, one of the best parts, we're also finishing on time. It is 5:30. Thank you very much for a great meeting. And until the next time, be epic. Thank you very much. And one more thing. I have people telling me, yes, you can buy us coffee. All the people in YouTube, all the people here, if you want us to keep the same level of energies, you can buy us a coffee. If you want us to enjoy a little bit of fun time, you can buy us a beer. Anything you want to do is over here, buy me a coffee, buymeacoffee.com/epic Photonics. Until the next time, the Epic team loves you. Keep going, Epic. Thank you very much. Bye-bye.
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 Bye, everyone.
Bye.
Good talk.